Hello and welcome to this part 2 of the vibrations lecture series. Part 1 was a basic introduction to the topic, outlining some basic terminology, some notation, and consideration of damping effects. In this part 2 we're going to use that knowledge now to develop some theory related to calculating the amplitude and the phase angle associated with mass spring damping systems when they have external forcing functions applied. It's strongly recommended that you viewed part 1 of this vibrations presentation before reviewing the contents of this presentation. So here's an overview of our vibrations in damping presentation. It's part 2. So to set the scene for this presentation, we're initially going to overview types of loading that can be applied to damp spring mass systems. As you will see, there are various types of loading that we can consider, but this presentation will only consider one type of loading. We then consider forced harmonics. That's the applied external continual disturbing force, which we'll denote as F0. We will consider phasor representation of kinematic properties. By that we mean the displacement, symbol X, the velocity, symbol V, and the acceleration, symbol A. And we'll see how this relates then to phasor representation of dynamic properties. That includes the spring force, Fs, the damping force, Fd, and the inertia force, Fi. We then construct a force vector diagram which finds the resultant external disturbing force, F0, in terms of the other three forces stated above. And from the vector diagram we'll be able to calculate the amplitude, symbol A, and the phase angle, symbol phi, that's induced due to the external force applied. The presentation concludes with a summary of nomenclature and formula derived in the presentation. Overview continued. Here are the approximate start times related to the various sections contained within this presentation to hopefully aid your ease of access through the presentation. But please note these are only approximate start times. So far in this ongoing lecture, we've only considered the motion of damp mass spring systems with no external disturbing forces applied. From a review of various textbooks used to generate this presentation, it's found that there are many different types of forces that can be applied to our damp mass spring system, and I'll overview some of them here. So these are forces applied to damp spring mass systems having 1 degree of freedom. So a first scenario would be a suddenly applied force. This would be an example of a mass suddenly added to the end of a vertical spring. A rapidly applied force. This tends to relate to instruments that are measuring, for example, variation in pressure. Applied steadily increasing forces. Such forces have a linear function of the form k multiplied by t, where k would be some constant and t is instantaneous time. Applied harmonic forces having constant magnitude. A typical function would be F multiplied by cos omega t. And the only type of force we're going to consider applied to our damp spring mass system of 1 degree of freedom is an applied force that has a magnitude proportional to the square of its radiancy, or the square of its angular velocity. So the forcing function we'll consider will be F is equal to m omega squared r. You may recognize that formula from previous presentation related to centrifugal force, and that relates to rotating or reciprocating masses where the amplitude is not constant but is proportional to the square of the angular velocity. Hence the force is equal to m omega squared r. So this is a scenario we'll consider in the remaining part of the presentation. Some textbooks consider applied complex harmonic forces. This relates to complicated pieces of machinery, but these appear to require the use of Fourier analysis. And also more realistic scenarios can be considered where we have damp spring mass systems but having several degrees of freedom, So these are applied harmonic forces. They can relate to, for example, multi-cylinder engines, where you have several forces or torques applied at different points in the system. So they're not one-dimensional. So as I said at the beginning of the presentation, vibrations is a vast topic area. There are textbooks written about this topic alone. So we're only really scratching the surface and introducing the subject in this presentation. So the rest of the presentation will only consider this one type of externally applied force shown here. Let's consider forced harmonics. So the following presentation relates to a mass capital M experiencing an applied disturbing force which is assumed to act continuously but varying sinusoidally with respect to time. So this is a continuous harmonic disturbing force. Let's consider the ideal system shown in figure 10. Here's figure 10. We have a main mass, capital M. Here is the main mass, capital M, suspended on a spring and damper, placed between the spring and the fixed support. Here's our spring, here's our dashpot damper. The main mass, M, is restrained in guides, so it only has vertical movement. This is termed 1 degree of freedom. Located on the main mass, M, is a small rotating machine considered to have an out of balance mass, lowercase m, and this is generating a centrifugal force of magnitude F0 is equal to m omega squared r. So for the particular instance shown, the angle theta here is F0. So at the position indicated in figure 10 and shown here, the component of the force F0 that acts vertically, don't forget the movement is constrained to vertical motion only, is F is equal to F0 cos of theta. That's shown in the diagram here. For the F0 applied at this particular instance, this angle theta, the vertical component of F0 would be F0 multiplied by cos of angle theta. So note that force F0 cos theta has a maximum value of plus or minus F0 and varies sinusoidally at a frequency, lowercase f here, of omega divided by 2 pi. That's termed the forcing frequency. Here's the angular velocity omega. Harmonic disturbing force continued. So what we note now is that the spring force is directly proportional to the displacement x. So the spring force is considered to be in phase with displacement, written mathematically as Fs is proportional to x. If we consider damping force, that's directly proportional to the velocity v. So damping force is considered to be in phase with the velocity, written as Fd is proportional to v. And the inertia force is directly proportional to the acceleration a. So again we say the inertia force is in phase with the acceleration, or inertia force Fi is proportional to a. Referring back to our presentation on simple harmonic motion of a mass spring system, for the x displacement shown from the equilibrium position, shown here on our plot of the displacement diagram, the displacement would follow this cosine curve, the velocity would follow this negative sine curve, and the acceleration would follow this negative cosine curve. That's as the mass travels this path during the oscillations. Just note that positive displacement is downwards. Harmonic disturbing force continued. So any disturbing force, F0, applied to the mass to induce movement must overcome the three forces stated on the previous slide. That is the inertia force, Fi, the damping force Fd, and the spring force Fs. Thus the disturbing force, the F0, can be considered the vector sum of these above three forces. So disturbing force F0 is equal to Fi plus Fd plus Fs. The inertia force is mass times acceleration. The inertia force is proportional to the acceleration. The damping force is the damping constant multiplied by the velocity. So damping force is proportional to velocity. And the spring force relates to the displacement. So the spring force is proportional to displacement. Now it's writing the equation in terms of displacement. That will be mass multiplied by x double dash, second differential of displacement with respect to time. That will be c multiplied by x dash, that's displacement differentiated with respect to time. And we have k multiplied by x. And again we have this second order differential equation in x. So the x dash is actually dy by dx, the velocity, and x double dash is d2y by dx squared, the acceleration. Now in our scenario, the mass is restrained to move vertically only, so it's only the vertical component of the out of balance centrifugal force that's to be considered. In other words, the cosine component from our previous figure 10. This vertical component here, which is the F0 multiplied by cos theta. So we write in the equation, left hand side, instead of F0 we have F0 cos omega t. Note that omega t is equal to theta. We viewed that in our previous simple harmonic motion presentation. And that's equal to mx double dash plus cx dash plus kx. So there's our second order differential equation where we have an applied external force to our damp mass spring system. A note for reference, I've labelled this equation 4. Harmonic disturbing forces continued. I've just repeated equation 4 from the previous slide. Now in equation 4, force F0 is considered to be a constant value. Its magnitude is unchanging. However, for the particular scenario that we're considering here, our F0 force is actually the centrifugal force, denoted as m omega squared r. So equation 4 above could be rewritten as shown below, where the m omega squared r now replaces F0. Call this equation 5 for reference. But in equation 5, the m omega squared r is no longer a constant value. It varies with the angular speed omega squared. So the forces in equation 5 can be expressed by their particular values at any instant in time. But as stated previously, these forces will not be in phase with each other. That is, the spring force is a maximum when displacement x is a maximum. The damping force is a maximum when velocity v is a maximum. And the inertia force is a maximum when the acceleration a is a maximum. So as stated, all the forces are out of phase with each other. Harmonic disturbing forces continued. Just repeated equation 5 for reference. So equation 5 is actually a vector sum, not an arithmetical sum. So that means each of the forces in equation 5 can be represented by a rotating vector, sometimes termed a phasor, moving with an angular velocity omega, where the length of the respective phasor is actually represented by the respective maximum force value. When analysing the effects of the forcing function F0 that's applied to our damp mass spring system, there are two main parameters that are of particular interest. The first is the maximum amplitude A of our system due to the effect of the applied disturbing force. And the second is the phase angle, phi, which is the lag between the disturbing force, F0, and the system response, x. So the following analysis will use phasor representation to derive equations for both the amplitude A and the phase angle, phi. So harmonic disturbing forces continued. Let's now consider phasor representation of the various forces being considered in our analysis. Now, from observation and indeed knowledge of such mechanical systems, we know that the main mass, capital M, oscillates vertically, and we assume that will be with sinusoidal oscillation, having an amplitude, capital A. From our simple harmonic motion theory, reviewed previously, the following relationships were derived. And these equations are actually extracted from the previous simple harmonic motion presentation. Displacement x is equal to A multiplied by the cos of omega t, where A is the amplitude. Velocity v, which is the first differential of x with respect to t, so can be expressed as dx by dt, or x dash in some textbooks. That's equal to negative omega a multiplied by sine omega t. In this case, the a omega is the amplitude of the phasor. And finally, acceleration, a, which can be written as the first differential of velocity respect to time, or the second differential of displacement respect to time, x double dash. That's equal to negative a omega squared multiplied by cos omega t. So for the acceleration, the a omega squared is the amplitude of the phasor. Harmonic disturbing forces continued. Phasors of displacement x, velocity v, and acceleration a are generically plotted in figure 11 below and figure 12 on the following slide. Here is figure 11. So again, these curves have been extracted from our previous SHM presentation, but on the left hand side of the diagram I've put the three phasors, and notice they're at right angles to each other. As the phasors are rotated, angular velocity omega, they remain at right angles to each other. But if we use the method of projections by plotting the various points of the respective vectors on our graph for the particular angle turn through, we can plot the various waveforms. And that's what's shown in the right hand graph. So the waveform for displacement x, shown here in blue, that follows a cosine curve. The waveform for velocity v, shown here in green, that follows a negative sine curve. And the waveform for acceleration a, shown here in red, follows a negative cosine curve. Harmonic disturbing force continued. Here's figure 12. And that shows again illustration of the displacement, velocity and acceleration phasors projected along the graph due to rotation of angle theta here. Notice the phasors have been shown move through angle theta, but of course they maintain their mutually orthogonal positions to each other. What the graph shows also is the maximum amplitudes. So maximum amplitude for displacement, shown here, it's A. The maximum amplitude for velocity, shown here, is A omega. And the maximum amplitude for acceleration, shown here, is a omega squared. We note this from the previous slide here. So from figure 12 it can be seen that for any specified moment in time related to a particular angle theta, we have the following kinematic relationships. Note velocity vector v leads displacement vector x by 90 degrees. So velocity vector peaks here, displacement vector peaks here, and that would be 90 degrees apart, or pi upon 2 radians apart if plotted against angle. We're plotting here against time. And the acceleration vector a leads the velocity vector v also by 90 degrees. So the acceleration curve peaks here and the velocity curve peaks here. And again, if plotted against angle, they would be 90 degrees apart here, or pi upon 2 radians apart. Harmonic disturbing forces continued. Figure 12 repeated here for convenience. If we now consider dynamic relationships, don't forget dynamics relates to forces involved with motion. We know that the spring force, Fs, is directly proportional to displacement, so it will therefore be in phase with displacement x. We know that damping force, Fd, is directly proportional to velocity, so it will be in phase with velocity v. And we know that the inertia force, Fi, is directly proportional to the acceleration, so the inertia force will be in phase with the acceleration a. So that means the spring force Fs, the damping force Fd, and the inertia force Fi can also be represented by phasors, also rotating with angular velocity omega in radians per second. So figure 13 just shows a generic overview of the three forces, and we can see here that the damping force leads the spring force. Again, if plotted against angle, that would be by 90 degrees. And we can also see that the inertia force leads the damping force. Again, that would be by 90 degrees or pi upon 2 radians if plotted against angle. So essentially, instead of having our phasors denoted x, v, and a, in terms of forces, we can now denote them as Fs, spring force, Fd, damping force, and Fi, inertia force, with Fi leading Fd and Fd leading Fs. So phasor representation continued. If we consider an instant in time that's chosen when the displacement vector is horizontal, and that's purely for convenience of analysis, the phasor diagrams shown in figure 14 can be obtained. Figure 14 is shown here, where diagram A shows the forces involved and diagram B shows the amplitude of the phasors. So imagine in figure B, our three kinematic phasors are rotating with angular velocity omega, and we take a snapshot of this motion when the displacement x is in the horizontal sense here. As I say, purely for convenience of analysis. But this displacement phasor x, which can now be considered a stationary vector because it's at an instant in time, has amplitude a. On the force diagram here, we know that spring force is associated with displacement, so Fs would be shown in the horizontal sense, where Fs is equal to the spring stiffness K multiplied by amplitude A. Back into figure B here, we know that the velocity vector v is 90 degrees around from the displacement vector, and that has amplitude a omega. So as we know that the damping force is in phase with the velocity, then the damping force Fd is shown in the same sense as the velocity, and damping force is the damping constant multiplied by A omega. And finally, 90 degrees around from the velocity, we know we have the acceleration, A, and the amplitude of the acceleration was A omega squared. We know that the inertia force Fi is in phase with the acceleration, so Fi is the main mass, capital M, multiplied by A omega squared. So now what we essentially have in figure 14a is a vector diagram at this particular instant in time. So we can use this diagram to help draw a force vector diagram from where we can determine the disturbing force F0. That process is shown on the next slide. Phase of representation continued. So from consideration of figure 14 on the previous slide, the force vector diagram shown in figure 15, shown here, can be constructed from which the resultant, that's the disturbing force F0, can be determined. So again, from a previous presentation related to force resolution, we can draw a vector diagram of our three forces applied. That's the spring force, the damping force, and the inertia force. If you remember from our previous work, it doesn't matter in which order we consider these force vectors, but we just draw them head to tail on a diagram. So in figure 15a here, I've commenced a diagram with force Fs, a spring force shown here. On the end of that, I've added the damping force Fd, and on the end of the damping force, I've added the inertia force. Again, it doesn't matter which order we had decided to draw the vectors. I could have drawn Fi first, then Fs, then Fd. I would still end up with the same resultant force, which is the F0 force, the disturbing force. In this particular analysis, because of the orientation of the vectors, we find that Fs and Fi can be subtracted. So in figure B here, I've simply denoted this bottom vector here as Fs minus Fi. And then that provides me with a simple triangle of forces. From this I can determine the magnitude of F0 by calculating the lengths of this vector. And I can also determine phase angle phi, shown here. Just note for reference, this diagram has been drawn with the spring force Fs assumed greater than the inertia force Fi. Of course, that doesn't have to be the situation. We could have a diagram where Fi is much greater than Fs. Just be aware that different shape diagrams can occur. But in all cases, we will end up with a triangle of forces because Fs and Fi are always in opposite directions to each other, so can always be subtracted. Phase of representation continued. Figure 16 below here shows the same vector diagram as on the previous slide in figure 15, but now the formula is stated for the respective forces. So this is the spring force here, the damping force here, and the inertia force shown here. What we're going to do now is use these respective forces to determine equations for the amplitude of the motion of our damped spring mass system when subjected to a disturbing force, and also to calculate the phase angle of the system. Phase of representation continued. So figure 16 on the previous slide, figure 16a repeated here, shows that the applied disturbing force F0 is at angle phi, shown here, to the horizontal. So it must be displaced by the phase angle phi relative to the displacement vector x. Applying Pythagoras' theorem to figure 16, figure 16b shown here, we have the square of the hypotenuse here is equal to the sum of the squares of the other two sides. So here's the base of our triangle squared, and here's the height of our triangle squared. The transposition process shown here looks quite lengthy, but that's because I've stated all the individual steps. So the first step on the right hand side, I look for my common factor a squared, So a squared is in this bracket and a squared is in this bracket, so taking the a squared outside of the bracket. Next, I factorise the right hand side of the equation on a squared, factorising the right hand side on a squared here. I've then divided throughout by m squared, so now every term gets divided by m squared. I just rearrange the right hand side here, put the m inside of the squared bracket. On this next line here, I simply cancel the m in the numerator with the m in the denominator to leave me with simply the omega squared term here. Note the relationships. We now let k divided by m equals to omega n squared. So replace this k divided by m with the omega n squared here. And we've also let c divided by m equals to 2 multiplied by zeta multiplied by omega n. So replace this c in m here with the 2 zeta omega n term. And finally I rearrange for a squared by dividing both sides by this bracket here. Here's an alternative form for a squared. I've simply brought the bracket from the denominator to the numerator, but of course raised it to the power of -1. So these two equations both calculate a squared. If you want to calculate the actual amplitude, of course, you have to square root both sides to find a. Phasor representation continued here. Using the previous relationships, omega n squared is equal to k divided by m, and c divided by m is equal to 2 zeta omega n, I can rewrite the triangle of forces as shown in figure 17, but now in terms of zetas and omegas. So the vertical side of our triangle is 2 zeta omega n multiplied by omega, and the adjacent side is omega n squared minus omega squared. So to find the tangent of phi, it's the opposite side of our triangle divided by the adjacent side of our triangle above. Of course, to find the actual phase angle phi, we'll use the inverse tan or the arctan of the opposite side divided by the adjacent side. And again, for reference, just notice that arctan is actually tan to the -1. Phasor representation continued. The graph over the page endeavours to illustrate the effect of phase angle phi on the response of our damped mass spring system. When the sinusoidal disturbing force F0 is applied to our system, the sinusoidal system response, displacement x, is shown to lag by angle phi. Just note, when plotted against time t as opposed to angle theta, the lag is calculated as phi divided by omega. This is shown in figure 18 on the next slide. Phasor representation continued. Here's figure 18. And this shows a plot of force F in newtons and displacement x in millimeters against time t in seconds. So we can see that the disturbing force here, F, leads the displacement here by phi upon omega. That's termed the lag of our system. So phasor representation continued. So figure 18 above generically illustrates the response of our damped mass spring system to an applied varying disturbing force F, both in terms of maximum amplitude, that's the maximum displacement x, shown here, and the system lag, the phase angle phi, between the applied disturbing force and the displacement x. So essentially we've produced an analysis of our damped mass spring system, so we can now determine the response of our system when subject to an applied disturbing force in terms of the maximum amplitude, maximum displacement, and the system lag angle phi. So here's a summary of all the nomenclature and the formulae we've used or derived so far, and which we will be using to solve the exercises to follow. So we have a main mass of our machine or system, which is capital M in kilograms. We have the rotating mass, that's the offset mass in our system, and that's lowercase m, also in kilograms. We have the displacement x, which will be meters. We have amplitude, maximum x, a, that's also meters. We have the spring stiffness, symbol lowercase k, or the Greek letter lambda, and that's force divided by extension, so that's F divided by x. Note that F can sometimes be the weight force associated with the main mass. And note in some questions, X can actually be the compression of the flexible supports on which the machine is located. And the unit of stiffness is the Newton per meter. I've called that equation 1 for reference. We have our spring force, Fs, that's stated as negative kx here, as it opposes the motion, and that's in newtons, equation 2. We have a damping constant, c, that's defined as the damping force divided by the velocity, as the unit of Newton per meter per second, or sometimes Newton second per meter, or kilogram per second. Labelled at equation 3. We have the damping force, Fd, which is negative c multiplied by the velocity v, and that will be newtons, equation 4. We have what's called the critical damping constant, cc, and that's calculated from the equation 2 multiplied by the square root of mk. Notice it's capital M there for the main mass or mass of the system. And there's also the damping ratio, normally stated as Greek symbol zeta, which is the damping constant C divided by the critical damping constant Cc. That's a ratio, so that's dimensionless. So they're equations 5 and 6. Summary continued. I've stated here various damping characteristics that we reviewed previously. They're just included here as a brief reference guide as to the effects of zeta on our system. Then we have the angular velocity of our offset rotating mass, that's lowercase m. Capital omega is used for RPM, and lowercase omega is used for the radians per second value. We have what's termed the undamped natural circular frequency, omega n, and that's calculated from the formula square root of k divided by m. That would be in radians per second. I've called that equation 7 for reference. And we have the damped circular frequency, that's omega d, and that's calculated from the equation omega n multiplied by the square root of 1 minus zeta squared. Again, the unit is radians per second. It's equation 8. There are some other terms that we sometimes refer to within this work. The damped frequency of vibration, eta d, is equal to the omega d divided by 2 pi. That's a frequency in hertz, equation 9. And the periodic time of damped motion, that's Td, and that's 2 pi divided by omega d. Remember from our previous work on sinusoidal forms, periodic time and frequency are the reciprocal of each other. Our summary continued. Just stated here the equation for amplitude squared. There are two forms. 11a shows the fraction form here, and equation 11b shows a squared. It's written on one line. I've now brought the denominator shown here to the top line, but raised it to the power of negative 1. And also tan of angle phi was 2 zeta omega n divided by omega n squared minus omega squared. Call that equation 12. Here's a summary of the maximum forces. Maximum forces occur at the maximum amplitude of our various phasors. So the spring force Fs is Ka, that's in newtons, equation 13. Damping force Fd, that's C multiplied by A multiplied by omega in newtons, equation 14. And the inertia force Fi, that's Ma omega squared, again in newtons, and that's equation 15. Here are the forces applied: spring force, damping force, and inertia force. they're all mutually orthogonal to each other. In other words, they're all at right angles to each other. Finally, for reference, I've included the ASTC diagram. This is a diagram we used in a previous presentation to solve trigonometric equations, and it helps us to determine in which quadrant angle phi would reside. It's not always in the first quadrant. And finally, before we review an example, here's some more reference information. The conversions from RPM to radians per second will be required in some cases, and to undertake that conversion, we multiply by 2 pi upon 60. And in certain questions, we'll also be referring to the quadratic formula, standard formula here, stated for reference. Here's the bibliography used to help generate this presentation. You've now reached the end of part 2 of the presentation related to our vibrations in damping lecture series. This was a particularly theoretical presentation, but I've tried to outline to the best of my knowledge of how damp mass spring systems can be mathematically modelled. Look forward to seeing you for presentation part 3 of the lecture series, where we apply the various formulas derived here to solve some practically orientated problems. Thank you for hanging in there. As always, thank you for viewing.